All right, so we're going to talk about the type of operations we could do with matrices. Not just solving for a system, but what we can do, like add, subtract, multiply, and we'll talk about division way down the road, but it's a little different when it comes to matrix operations. But the main three itself. So how do we add, subtract, and multiply matrices together? Okay. So first thing, how we're going to do or define a matrix itself is this type of notation. So we're going to let A be a matrix with an ith and j column, be an n by n matrix, and let B, again, same process where these are the entries of the ith and j component, be an r by s matrix. We say A and B are equal, meaning both, they have the exact same portions, m and r the same, and s the same, so same rows, same columns, and each identically entry is the same, which makes sense, right? They're just a copy of each other. Okay. So now let's actually get to the main part. So first we'll talk about addition and then scalar multiplication. So the first thing is, how do we add matrices? So how to add A plus B? All we're going to do is add each individual entry together. Okay. Next part is multiplication, is scalar multiplication. So again, given a matrix A, any n by n matrix, and then the product R times A, where R is a scalar, we just multiply R by every single entry in A. Okay. Now, the theory is much more complicated than the actual, portion. So, for example, why don't we just try some practice problems so you can see how this is going to work out. Okay, so we're going to add A plus B. So here's matrix A, here's matrix B. Okay. So all we're going to do is going to add entry to entry. So what I mean by entry to entry is, well, this is in the first row, first column, and we add it to the first row, first column of the next one. That's what I mean by entry to entry. So 6 minus 2 is 4. 8 plus 4 is 12. Next is going to be 7, and then finally negative 3. And there's our answer. Okay. Now let's go on to B. A plus C. Okay. So we do have a bit of a problem because notice these entries only stop here. Okay. So at this point we got to go back to the definition. Okay. Now, when it comes to the addition of two matrices, they both have to have the same number of rows and the number of columns. If they both don't have the same number of rows and same number of columns, it's not possible. So you can't actually add them together, so I just put not possible. No solution, right? There's no such thing as no solution. Just it's not possible to actually add these together. So we can have an actual addition, or not possible because we can't do that. Now same thing applies for C. So C is B plus C, which again is the same thing as part B, so it's also not possible. All right, so those are freebies. Let's move on to D. So D is just 3 times C. So here C, we're just going to multiply by 3. And usually, just like a distributive property, we're just going to distribute to every single entry within C. And there we go. And now the last one for E, it's a little different than A because there's the 2 there. So we're going to matrix A plus 2 times matrix B. So I'm just going to copy A down and distribute the 2, and then just add them together. And there we go. So adding and multiplying by vector or by scalar is actually pretty straightforward. The fun stuff comes into play, right now, because now it gets a little bit trickier when it comes to different things within the matrices. Okay, so first I'm going to talk about vectors in matrices. So thing to do is, like, remember, we're talking about vectors, right? These are individual vectors we talked about before. So any type of vector can be created into a matrix. Okay, it's a very weird matrix, but can technically become a matrix. So let's suppose we have this vector here. Okay. So this being an nth dimensional vector, we can create a matrix using this vector being a 1 by n matrix, or n by 1 matrix. So this vector v is going to look like this. So instead of going this way, we're going down. So it just becomes a column matrix. Like I said, this is going to be an n by 1 matrix. Now, usually, again, when we talk about solving for a system, when we talk about later on, most of the time we'll have like the actual answers for x being also as a column matrix. So x1, x2, all the way xn as well. So we'll be using this notation as well once we solve for systems. Okay. So in general, the nth dimensional vectors are real components and it's called the Euclidean nth space, or denoted as Rn. And this is very usually universal to signify your nth dimension. So you're just an infinite, basically. So it just goes on for forever. So again, this means that the solutions go on for a very, very long, or just look like this. Okay. So now the question becomes, well, we could solve for a system like we did before, but how do we use this type of notation to show it? Okay. So we have this matrix, and we just want to express the solution as vectors now, meaning like this. So it's already broken down because we have 1 and 1, so it's already in a row echelon form. So we're going to have, looks like, remember this is going to be our, and it's also a homogeneous equation. So we're going to have x1 minus 3x1, 2, 3, 3 plus 2x4 equals 0. And we're going to have x2 plus 3x3 plus x4 equals 0. Okay, so notice they both have 3's and 4's in common, so if we bring those on the other side and solve for 1 and 2, we now have that. Okay, so this is how we're going to express it in vector format. So I'm going to do x vector, so I'm going to have 4 different vectors. So I'm going to have x1, x2, x3, and x4. Now, we have 2 independent vectors and 2 dependent vectors. Okay, so I'm going to write exactly what each vector represents. So x1 is equal to 3x3 plus 2x4 minus 2x4. Should be a negative. Sorry. There. x2 represents negative 3x to the third, or sorry, 3x3 minus x4. Now, for the rest of them, it's just going to be x3 and x4, because now these are independent, so I can pick any ones I want for that. Okay. So there's 2 ways to express it. This is the OK version. That's good for now. The more advanced version, we'll talk about that much more in detail, and the proper way, I guess we call it, is expressing everything in terms of just your independent variables. Okay. So for example, if I factor out x to the 3, x3. So if I factor out x3 from every single one, so I get, so for example, factor it out, what is left over? 3, negative 3, 1, and 0. Right, because there's none in there. Okay. Now I'm going to plus, and I'm also going to factor out x4. So if I factor out x4 from each one, I get now negative 2, negative 1, 0, 1. Okay. Now notice, if I put these in, again, and I add them, I actually get that back. Okay. So this is the proper way to actually solve or show a system or express a system in vector format. This is the okay version, this is the actual proper breaking down of it. Okay. So let's try another example using that same template. Okay. All right, so let's see, we have, good, so it's already rational form, so we can start from there. So I'm just bringing it, so I'll just do the work for you guys. So this is so 1, 2, 3, 4, 5. Okay, 2, 3, 4, 5. Okay. X3 plus 6x5 equal -3, and then x to 4 plus 3x5 equals -5. Okay, so it looks like 5 for sure. We're going to bring that over. So we'll just solve for x1. We'll solve for x3 because the 5's in there. And again, solve for x4. There we go. All right, so now we can do the same process we did on the last example. So this is the same thing of x1, so I'm just going to write that all out. X2 is, so we have two independent variables. So all these are going to have x2s and x5. So this is going to be a x2, x3, x4, and x5. All right, so like above, this is going to be a combination of two different vectors, x2 and x5, with another one we'll talk about later. Okay? But for now, let's do the ones we can copy above. So we're going to have x2. When I factor that out, it's going to be -2, 1, and the rest are 0 because they don't have any x2s in your solution set. Plus x5. So this is going to be -4, 0, -6, -3, and 1. Now, let's talk about the constants. Okay. So remember, we're expressing everything in terms of vectors. So it's going to be plus the constants themselves. We don't have to put a c, it's just literally just the constants. So if you notice, it's the exact same template. We're just breaking it apart into individual terms. So now it's just going to be the constants. So 2, none here, so 0, -3, -5, and then 0. And there we go. There's our expression there. Okay, so we've gone through adding, and basically the same thing for subtraction, and multiplying by scalars. We've gone through expressing our solutions into vectors format. Now we're going to talk about how in the world do we multiply matrices, because this is a little bit more complicated, just simply just adding and subtracting itself. Okay, so here is the theoretical one, and we'll talk about a shortcut to it. So let A be an n by a matrix, and let B be an r by s matrix. If r equals n, then the product of AB is M cross S matrix. So I always do it this way. So we have an M cross N, that's matrix A. So I multiply A times B. B is, so if it equals, it'll be N by S. The only way we can multiply matrices if these two are the same, which means the order in which these do actually matter. So you can't actually flip these around. So it has to be actually defined, and that's the key thing. Okay? So it goes this way. So you can't just flip-flop like, cumulative property when it comes to multiplying numbers normally. So if these are the same, your product is going to be m by s. That's what this represents. Okay? So each entry of AB is the sum of A's row by B's column. Okay? So this is the row, and this is the column. You're wondering, what in the world is that talking about? What does it mean? So, I'll give you guys a simple example. So let's suppose this is matrix A, and this is matrix B here. Okay. So what I'm going to do is all of these numbers, I'm going to multiply entry to entry down here, like that. So this times that, that times that, that times that, and so forth. And then I'm going to take the sum of all of those, and that's going to be the very first entry of AB. So it's a lot more complicated than AB. Okay? So let's just do an example so you can see how this little cheat sheet will help you out. So find the products of AB, BA, and all the rest of them. Okay? So we'll just go down the list. A, B first. Okay, so this is a 2 by 3 matrix, and this is a 3 by 2 matrix. So since the inners are the same, I know my product is going to be a 2 by 2. Okay, so let's try this out. All right, so how this works is I'm going to multiply 1 by 1, negative 4 by 5, 6 by 2. I'm just going to write that here. So 1 by 1 is 1, negative 4 pi is negative 20, and this gives me 18. Or no, 12. What am I doing? 12. So now I'm going to add all of these three numbers together, and that's going to be the first entry in this one. And I do that for every single portion. So it's the row by column. So now it's going to be this row by that column. Okay. Now, we never go down, we go this way. We're going to go across first. So the next entry here is going to be now the exact same row by the new column over here. So 1 by 3 is going to be 3 plus negative 4 that pi is going to be positive 8. That by that's going to be 6. That's my next entry there. Now I do the bottom two using the bottom row here. So rinse and repeat, but I'm going to use this row with the same columns down. So that gives me 2, positive 20, 16. And then we can do the last row. So negative 8. And then 8. Right, yep, 6, negative 8, plus 8. Good. And now I just add them all together. All right, so this is going to be 13, so it'll be negative 7. This is 9, so 17. This is 18, so 38. And this is just going to be 6. So this is A, B. Okay, so now we're going to do the opposite, BA instead. Okay, so this is a 3 by 2, and this is a 2 by 3. So it works because the 2's cross. So my result is going to be a big 3 by 3 matrix. Okay, all right. Okay, let's see what we get. The good thing is this one is not too large because it's just two columns. So 1 times 1 is 1. 3 times 2 is 6. So that's my first entry. Again, you're going always across this way. Next one is going to be negative 4. Plus 12. Next one's going to be 6 plus 24. Okay, now the middle one. So 5 minus 4. Negative 20 minus 8. 30 and 16. And now the last one. There we go. All right, and then we just add them together. So 7, 1, 4, negative 2, negative 28, negative 4, 30, 14, and 20. And there we go. Okay. All right, a couple more to go. So now next is BC. So it does work. So the result is going to be a 3 by 2 matrix. Okay. So good thing is this is also pretty short because it's going to cross. So 1, 1 is 1 is 15. Negative 2, 12. Now we do the middle. And now the bottom. And there we go. Okay. All right, let's do CB. Now you may think this is a lot of work, right? So before we write everything down, let's see if it actually does work, right? Because it's got to be some of these don't work. I mean, I'm just trying to trick you here. So CB, so C is a 2 by 2. and B is a 3 by 2. So notice it does not work. 3 and 2 are not the same. So again, just put not possible. Okay. Now, what about CA? So both A and C are, well, A is going to be, so let's see. We have CA, so this is a 2 by 2 for C. And A is a 2 by 3, so it will work. This time our result is going to be a 2 by 3 matrix. So 2 columns, 2 rows, 3 columns. All right, so let's see. So first we write C, which is there. And then A. Okay. So again, this is going to be a 2 by 3, so 2 rows, 3 columns. So first entry be 1 minus 4. Next entry, negative 4 minus 8. And the last one, 6 minus 16. And now we do the middle, the last one, last row with each column here. So 5 plus 8, negative 20 plus 16, and then 30 plus 32. No, yeah. And there we go. Long process to multiply matrices together. Okay. All right. So we'll have more practice on multiplying. But again, this is just operations, right? What else can we do with matrices? So we already had a lot. So now what we can also do is using the vectors, we can express stuff. So express systems and so forth in that nature. So for example, we have a lot of systems here. We have a system, we have a 3 by 2 system here and a 2 by 2 system there. So what we want to do is express the linear systems in the matrices such that the x values are only in terms of z. So in other words, bypass this y stuff completely. Okay. All right. So the nice thing about multiplication and matrix multiplication. Okay. So let's see. Let's rewrite this kind of format here. So we're going to express this on the coefficients of y. Okay. So we're going to write x1, x2, x3 equals, and we're just going to go across. Okay. So look at 3y1. I'm not going to put y1 for now. And then, well, yeah, I'll talk about that. So we'll just use its coefficient matrix. So how about that? Yeah, let's just do that. So this is going to be our coefficient matrix. So negative 1, 3, and then 2, negative 4, right? This is our coefficient matrix. Now, I'm going to multiply by this other matrix here. Because when I do that, I get exactly this back. Okay? So that's how we express matrices when it comes to a system of equations. And I'm going to do the exact same thing on this side. Okay, same thing, coefficient matrix, now with z's in. And again, multiply by this matrix here. And again, we talked about this earlier. I'm just going by the column matrix. just like that. Okay, so my goal is to have these numbers, or these letters, only represented as these ones. So what are we going to do? We're going to multiply them. We're going to multiply these two matrices. This is a 3 by 2, and this is a 2 by 2, so it does work, and the result is going to be a 3 by 2. So we're going to multiply these coefficient matrices together. Okay. And do the same process we did above, so row by column. Okay. Now, so these are going because what we end up doing is we're substituting all of this right there. So that's why we multiply the coefficient matrices. And what's attached at the end is the z. So now if I redo this and go back to its non-matrix format, we now have x1 is equal to 11z1 plus 5z2, because remember these are just the coefficient matrix. x2 is equal to 6z1 plus 3z2. And then finally x3 is equal to negative 10z1 minus 2z2. And there we go. All right, now let's get to the solving part. Okay, so in general, any system of linear equations can be created or formed using vectors. In other words, matrices or matrix vector representations. Okay, so given our arbitrary system of equations, okay, I can represent this using matrices vectors. Again, using its coefficient matrix, so just these numbers themselves, times the x's and then this is equal to just a column of b's. So this and those are the same. It's just another representation of it. Which means we go to our very special different way of representation of solving for a system of equations, or solving for the x variables. Solve for the matrix equation ax equals b, which is exactly that, a times x equals B, the vector B, given that A and B are those. Okay. So how do we do that? We just combine these like normally. So again, this goes back to just solving for a basic system. The only difference is we don't first convert it to a matrix and then solve for it. We just attach it automatically. So what I mean by that is just bring A here, and set them equal to B. So 2, 6, and 6. And just solve normally, right? So get the our good old identity property here, right? So we want 1, 0, 0, 0, 1, 0, 0, 0, 1, right, on this side itself, or as best as possible on that side. Okay. All right, so let's try this out. So let's see. I already have a 1 there, which is great. So let's see. Why don't we just do R2 minus 2R1 to get rid of this 0 here. So it'll be 2, 6, and negative 2 and 4 if I multiply by 2. Keeping row 1 the same. So this makes that. So 2 minus 2 is 0. 5 minus 6 is negative 1. Negative 1 plus 2 is positive 1. And then 6 minus 4 is 2. Okay. I'm going to do the same thing for this 2 down here. Oh, write this down here. Okay. Okay. So 2 minus 2 is 0. 8 minus 6 is negative 2, yep. And then negative 2 plus 2 is 0. And 6 minus 4 is 2. Oh, here we go. Sorry, 8 minus 6. So this will be positive 2. Not the other way around. Okay. And then this is good. Good. Yeah, right here. Now we're on the spot. All right. So let's keep going. Right. So we have this 1 here. So I'll keep it in that spot. So I'll make that 0. Make that 0. So again, same process. So I'm going to do, I'll do the top one. So row 1 plus 3 times row 2. So if I multiply row 2 by 3, it'll be 0, negative 3, 3, and 6. And what I'm going to do now is I'm going to divide this by 2. Now I have that. Okay, so now notice this is already done. So this is actually the middle one. So I'm going to flip it around just for my practice sake. So we already have one answer. Okay, so you know x2 is equal to 1. All right, so now I just got to get rid of this one. So it looks like it just adds straight down. So row 2 plus row 3. Okay, so now we got 2 down. One more to go. So it looks like row 1 minus 2 times row 3. So it's going to be 0, 0, 2, 6. 2 minus 2, 0. 8 minus 6, 2. So therefore, our vector representation will be 2, 1, 3. Remember, that means x1 is equal to 2, x2 is equal to 1, and x3 is equal to 3. Okay, so now that we have understanding, guess what? Let's just throw you for a loop here. So what I mean by that is, okay, what else can we do with this? Well, sometimes it can be a little tricky itself. Okay, so this is alternative forms, and what I mean by alternative is optional, right? But it could be useful as we go along in the sections. So alternate forms of matrix representations. So given n by n matrix A, the matrix A can be written as A equaling A1, A2, A3, A4, where each individual one is a column of the actual matrix. So it kind of looks like this. Okay? So then A1 is going to be the next column, next column, next column, next column, next column. Okay? That's what that represents. Now, there's the other one. So let A be this type of situation, and the jth column of AJ, and let X be a n by 1 column vector, so looking like that. Then the product of AX can be expressed as a linear combination. We'll talk about linear combination way down the road, but a sum of each one individual, which kind of makes sense, right? All I'm doing is doing x1 times this n by 1 matrix, or n by n matrix, and so forth down the road. Okay? But again, the theory is much more complicated than the actual application of it. So why don't we just try a simple example so you can see how does this work out. Okay? All right, so given the matrix A and X, being 1, 2, 3, A, write it in the form A equals those portions. Okay, so A1 is going to be literally just the first column of it. So it's just the 2 by 1 matrix, 1, 3. A2 is going to be the middle one, 3, 0. And then finally, A3 will be the last column, 5, 1. That's it. That's all it represents like that. Pretty easy, right, when it comes to it. Yeah. So now for B, we write it as AX. So all this is we're going to follow this template right here. So it's going to be x1 times a1, so the vector 1, 3, plus x2 times the vector 3, 0, plus x3 times the vector 5, 1. And we're done. Okay. So this is not one of them, but let's suppose we had a C term and say, what if I want to find or give a particular solution? Okay. So that means we get to choose. I'll choose 1, 2, 3 to be x1, x2, x3. So now when I do that, I'm just going to plug it into here, and we get AX is equal to 1A1 plus 2A2 plus 3A3. Kind of like that. So we have a system of equations with matrices now, not just numbers. So, because of what we have so much in these matrix representations, all that fun stuff, there are multiple ways now I can ask you to solve for the system. Not the basic general one where it could just give you a system and just going to convert to matrices and solve it. I can give it to any of these forms. So for example, I can actually solve for the system and give it to you in this way instead. Well, what does that mean? All this means, if I put everything together right, this is A1, A2, and A3, and this is just B. So I put the original matrix A together, we just solve for that, which we did earlier in the last example here, right? So we did all that work, but just showing you I can ask you in a different way now. So we got these answers earlier. So we found that eventually x1 was 2, x2 was 1, and x3 was 3. So if I asked you to express the answer in this form, you would have, well, x1 is 2, so it would be 2 times a1, so times this vector, plus 1 times a2, plus 3 times a3, equals b. There we go. Now, the very last thing is an alternative. Again, this is a very alternative way to do matrix multiplication. Okay? It's using the way we break stuff down like this. Okay? So this theorem says, let A be an n by A matrix, and let B be the matrix where it's already broken down B1 through BS's, be an n by S matrix, whose kth column is BK, so some random column is BK. Then the jth column of the multiplication of AB is A times the column of B, J, so that AB is equal to each individual one itself. Or in other words, the original A by its individual column portion. Again, the theorem is much more complicated than it actually thinks about. It's pretty straightforward. So let's just try this out. You can see. So notice this is always going to be A no matter what. So we're always going to be using matrix A. So this one. Okay. And we're going to use its individual B1, B2, B3 portions for the B term. So for example, B1 is going to be 1, negative 1, B2, 3, 2, and then B3 is going to be 3, 4. So this alternative way to multiply matrices is going to look like this. So it's going to be A, so 2, 4, negative 2, 1, times B1. Okay, that's going to be the first one. Next one again is going to be A times B2. And the last one is going to be again A times B3. Okay. And this works because, right, this is a 2 by 2 and this is a 2 by 1. So the result is a 2 by 1 matrix. So if we multiply again, right, so that by that, we get the matrix 4, 3. Multiply these out. This gives you 2, 14. And then multiply these out gives you negative 2, 16. Okay. Now remember, what are these? These are entries A, B1, A, B2, and A, B3, which are those definitions right here. So if I put them all together, A times B is just going to be the 4, 3, 2, 14, negative 2, 16. There we go. So again, just an alternate form. So if you like the old way of multiplying, go ahead. But again, I'm just showing you there's multiple ways to solve for a system and to multiply matrices now based off, what you really like itself.